Everyone, my name is Ahmad Siddiqa. So this is the question that we received as part of the design and analysis of algorithms assignment, which is campus route optimization using the Floyd Warshall algorithm. So basically, what happens is suppose that this is a college and there are multiple buildings in a college. So we'll assume that canteen is one building, hostel is one building, library is in one building, and admin block is in one building. Now what happens is there are different paths to go, like from one building to another, and the distance from one path to one building to another is denoted by their weights, which is going to be further explained by my friend who is going to show you the exact mathematical working of this. uh, what happens in Floyd Warshall, which how it dominates over Dijkstra's, is that you can have negative weights here. In Dijkstra's, you cannot have negative weights. In Floyd Warshall, you can have negative weights, but there should not be a negative weight sum cycle. So the further mathematical explanation will be done by my friend.
Hello everyone, my name is Hemant and I'm going to explain the Floyd-Warshall algorithm. So, the aim is to find the shortest path between every pair of buildings. Here the buildings are the vertices, roads are the edges and the distance matrix which will store the shortest distances. So, as we can see in the image, there are three buildings, that is A, B and C. So from A to B there is a road. As we can see in the image, there is a road which is having a weight of 4. And in the same way from B to A there is a road which is also having a weight of. So in the adjacency matrix we can see, as there is no path from A to A, from A to A, so since there is no path, the value will be 0. And we can see there is a path from A to B, so its value, the weight from A to B is 4, so the value will be 4. And we can see from A to C there is a path which is having a value of 10. In the same way the matrix is filled. Next we will see the core formula, that is d of ij is equal to minimum of d of ij comma d of ik plus d of kj. So here d of ij is the current shortest distance, d of ik is the distance from I to k, d of kj is the distance from k to j. So we will choose the smaller value between d of ij and d of ik plus d of kj. I mean to say that I will choose the smaller value between the d of ij and the sum of d of ik plus d of kj. Next one, the important one is the algorithm. For k equal to 1 to v, for I equal to 1 to v, for j equal to 1 to v, distance of ij is equal to minimum of distance of ij comma distance of ik plus distance of kj. So as I said before, this is the core formula. So I have to choose the minimum distance between the current shortest distance and the sum of distance from I to k and the distance from k to j. Next, let's take an example. So let's take the reference of the image that we took in the beginning. So the current distance is from A to C, that is 10. So the distance from A to C but through B is 4, and from B to C it is 3. So the total distance that will be from A to C through the B will be 4 plus 3, that is 7. Since the 7 is lesser than 10, then I will update that from A to C it will be 7. The distance will be 7 because we have to choose the smallest value. So we want the shortest path. That is the reason I chose the distance from A to C as 7. And the key idea here is uh, consider every vertex as an intermediate vertex. If the traveling through that vertex gives a shortest path, then update the distance matrix.
Hello, my name is Alan D'Souza. Now I am going to explain Floyd Marshall algorithm. The main aim of this project is to find the shortest route between the different buildings on the campus and display that route on the map. In this project, there are 6 locations. A means admin block, E means engineering department, L means main library, S means science labs, D means student dormitories, R means student sports arena. These locations are represented as nodes in the graph. The distance between the connected locations are stored in the matrix called adjacency matrix. If two locations are not directly connected, the distance is set to infinity. The most important part of this project is Floyd Marshall algorithm. This algorithm finds the shortest distance between every pair of location. It checks whether going through another location gives the shortest path and updates the distance accordingly. When the user selects the starting point and the destination in this program, the starting node is L and ending node is R. The program calculates the shortest route and total travel time. It then displays the route on the campus map and highlights the path with the animation. The project also includes iterative features such as clicking on locations, selecting locations from drop-down menus, views the Floyd Marshall matrix step by step, and automatically playing the algorithm process. In conclusion, the project uses the Floyd Marshall algorithm to efficiently find the shortest path between the campus building and provide a simple and iterative way to user to navigate the campus. Thank you.
Greetings everyone, myself Abhishek, and today I'm going to demonstrate our project called Campus Intelligent Suite. So this basically has 2 modules. The module 1 is string algorithms and the module 2 Campus Route Optimizer, which uses Floyd Warshall dynamic programming algorithm. The second module, Campus Route Optimization, is the problem statement is to find the shortest path between the buildings inside a campus. So here you can see there are campus and there are buildings, that is library, admin block, etc. So the campus is presented as a weighted graph. Buildings acts as vertices and roads acts as weighted edges. So here you can see it's the road which acts as weighted edges. Here there are weights. You can see the 5 kilometer or 5 meters or 500 meters, etc. So the algorithm is, if a shorter path is found from source to destination, if a shorter path is found, that marks the distance of the matrix gets updated. The process is repeated for every vertex. Suppose we come from here to here and go from here to here and go from here to here, and the algorithm checks whether traveling through an intermediate vertex provides a shortest path. So here the best case time complexity is order of VQ and the worst case time complexity is order of VQ. So the V is number of vertices. Since Floyd Warshall always uses 3 nested loops, the complexity remains same, that is order of V cube in the all cases. The project also displays the route of highlighting intermediate Floyd Warshall matrix updaters, helping users understand how the shortest path is calculated. So here you can see we can select the start point and the end point, and the route gets updated here. Also we can select the start point here and the end point here, and the route gets updated here. And this is it about our 2 projects.